Hi everyone, my name is Kayon and I made this video to help other students to solve a two-dimensional heat and momentum transportation on a flat plate. I made this PowerPoint to address the concepts and the geometry of the problem. The finite difference method is one of the numerical methods for discretizing the differential equation and finally approximate the solution of these equations. For flow problems, these differential equations include continuity, Navier-Stokes, and energy equations. And in this method, the derivative of a function is approximated by their equivalent differences, and a repetitive process with sufficient and optimal steps performed to approximate the desired function. There are three discretization methods named forward, central, and backward, as you can see here. To simulate flow on a flat surface that receives a constant thermal flux, velocity, and temperature are studied as unknown. To obtain these unknowns, the Navier-Stokes equations and the energy equation and the continuity equation will be used as was mentioned earlier. For this case of flow, it can be assumed with a good approximation that the solution area is two-dimensional and also the density is incompressible. Also, the flow is steady and the velocity and temperature of the far-field variables will not change over time. According to these assumptions and using dimensional analysis, it is possible to achieve a simplified form of equations that are known as boundary layer equations. Some of boundary conditions are at solid wall, no slip condition means U equal 0, wall temperature equal TW, and infinitely far from the solid wall we have a uniform flow, which means U equal U infinite, and uniform temperature means T equal T infinite. I need to mention that the discretization and approximation will be conducted by using central discretization method. In the correlations means above, the dx and dy are the distance between next grid respectively in the direction of x and y. But in the first order derivation we can't use central method, so we should use forward method since we don't have I-1 point and value. At the end, the discretized model of Navier-Stokes equation would be like this. As you can see here, we have the discretized model of the Navier-Stokes equation based on our former approximation, and after that we can get the values of Vig with the help of the continuity equation. To discretize the first derivative form y, the backward method would be used at the point I+1, because this point must replace the velocity in the direction of y in the Navier-Stokes equation, as you can see here. But for the first derivative in the direction x, the Crank-Nicolson method is used to calculate the average arithmetic values of velocity. After discretizing Navier-Stokes equation, we would discretize the energy equation with the same model, using the forward method for the first derivative in the x direction, central method in the y direction, and the central method again for y direction for the second order derivation. After that, we reach the stability problem. One of the key factors in solving PDEs is observing stability, which leads to convergence. For calculating the boundary layer formation, we use this report, which is a comprehensive reference for the heat and fluid transportation in engineering problems. Alright, now we are going to Matlab code and we try to write the equation that we discretized earlier. And for that we open a script, a new script. We save as a new file. Alright, we start writing CLC and clear and long format for the beginning. Then we define inputs. In the beginning, we start with defining a UI, which is the free stream velocity, and the user would define this and in the first place. I am going to write some of the recommendation in the input string. In the second sentence, we define inlet temperature, which is 25 degrees Celsius, which means that all the variables and the properties of the air should be defined in this temperature. So we define first properties of the air, which is new, in the temperature of the 25, which is 1.6 multiplied 10 power minus 5, which is the kinematic viscosity. After that, we define the length of the plate, and we define as 1 meter. Next, we define Prandtl number, which would derive from In the next part, we define Prandtl number, which is 0.71 for the air. A, which would derive from dividing nu to Prandtl number, is our thermal conductivity. The constant heat flux, which is Q, equals to 2100. In the next part, we define Reynolds number, as it is obvious, UI multiplied X divided by nu. K is the thermal conductivity of the plate, which it has been assumed 0.0255, related to the aluminium. Alright, after defining inputs, we need to check the turbulence condition, since all the discretized equations are based on laminar flow. So we write an if condition and define a warning for the user. So if the Reynolds is more than 5.10 power 5, we order to send a warning to the user that this laminar, this calculation must be changed, because it is based on laminar flow, and the current condition is turbulence. And write the end. After that, we define y, and which is the horizontal distance from the plate, and we set that as 0.025. After that, we are going to defining the boundary layer thickness, since we want to know that this boundary layer has how many percent of the horizontal distance of the plate and the stream. So psi is 4.92 multiplied by the Reynolds number, in the power of minus 0.5. In the next line, we define SO, which is the percentage of the boundary layer formation of the horizontal distance of the string. After all of these inputs, after defining these inputs, we need to generate the grid, and for that we define Imax and Jmax, which are the number of grids in the X and Y direction, which should be defined by the user. So we write an input code, and we ask that from the user. Same thing for the Jmax, which is the grid in the Y direction. And then with the help of Imax and Jmax, we are going to calculate the dx and dy, which are the distance from the next grid and the last grid. We define h in the next line, which is the convective coefficient of the air, but since the temperature are changing rapidly, so we have between 28 and 22. In the next level, 5 matrices which are the initial values of u, v, x, y, and t will be defined. Last part of definition is defining boundary conditions. In the second line is the defining no slip condition. Third and fourth are the u infinite, and in the first and last point in x direction. V is 0 to help having one direction velocity problem in the beginning, and T is a T infinite in the initial condition and in the end. After defining the boundary conditions, we should enter the main code, which is the discretized equation of Navier-Stokes and continuity. So in the beginning we define a main 3 loops, which the first one is the iterative loop, the second one related to the j, and the third one related to the I, which are the iterative for the x and y directions. So we enter the equation of Navier-Stokes, we discretize in the PowerPoint, and we write u I plus 1j equal to uij plus nu uij plus 1 minus 2 multiplied uij plus uij minus 1 multiplied by dx divided by the uij multiplied by dy power 2 minus uij plus 1 minus uij minus 1 multiplied by Vij, which is the velocity in the y direction we derived from the continuity equation. Vij multiplied by dx divided by 2 multiplied uij multiplied dy. So this is the Navier-Stokes equation that we derived earlier. For calculating the Vij, we write the continuity equation under this code in the next line. So Vi plus 1j equals to Vi plus 1j minus 1 minus 0.5 multiplied dy multiplied ui plus 1j minus uij plus ui plus 1j minus 1 minus uij minus 1 divided by dx. So this is the all Navier-Stokes and continuity equation that we try to solve coupled and together, since they are both related to each other, and we need to solve them in each iteration. After that, we enter the energy equation, which has 3 loops again, like the Navier-Stokes equation, and we enter the Ti and 1 equals to Ti and 2 plus Q divided H, H1 and I, which are the energy equation on the plate condition, and the transporting heat from the plate to the air above the plate. After that, we write the energy equation, which is Ti plus 1j equals to Tij plus A multiplied Tij plus 1 minus 2 multiplied Tij plus Tioj minus 1 multiplied dx divided by uij multiplied dy power 2 plus Tij plus 1 minus Tij minus 1 multiplied Vij, which we derived earlier, multiplied dx divided by uij multiplied 2 dy. That is that. In the third line, we write the equation to calculate the end of the plate, which is a Ti max and 1 in the first place. After entering the equation, we write the Nusselt and CFD equation to help the user obtain these values in any length of the plate. So we define an input to ask the x value from the user and desirable position, calculating Nusselt and CFD. And the report is from the Bachelor Thesis from Sanders, and if we go to page 25, we can we reach to the empirical CFX and Nusselt and write them into the code. Under the empirical codes and equation, we have the numerical equations, which help us to understand how many % of error do we have. So we define a new Reynolds, and we write the CFX, empirical and the numerical. In the line after that, we define an empirical Nusselt number and the numerical Nusselt number. Alright. As I mentioned earlier, one of the key factors in PDEs is stability. Then we try to find the smallest value of the U which is the velocity in x direction, and calculate the new value of dx based on the stability equation. So we need to understand what is the smallest positive value of u we derived earlier by the Navier-Stokes equation. So the trick is that the new value of dx, which is defined by r, should not be smaller than dx we defined earlier in order to have the current stability condition. So if the new dx, which is defined by r, is smaller than dx, we sent a warning to the user that Imax or Jmax is declining stability condition, and check the another grid generation. After defining all the codes from Navier-Stokes and energy equations, we need to display our results. So for presenting u and t, we go to counter f u25 and counter f t25. If we run this simulation, and for the stream velocity 7, x direction 500, y direction 50, and if we want to calculate this, we can have these contours. You can see the left is the plate, and it will start from the bottom. The stream starts from the bottom, and the maximum temperature is 500, and the velocity has more than 6. So you can see here that this blue and in the right in the T temperature contour is the free stream velocity, and these are actually the boundary layer formation. You can try more based on your resources and computer's capability, you can try smaller values of dx and dy and smaller grid generation. Thank you for your watching.